Welcome back for the second talk of this morning by Donggyu Kim about Baker-Bonus theory for Lagrangian Grassmannians.
Thank you for the first So also, yeah, it's great honor to give my talk at here. Yeah. Okay, let's start. So the previous talk, Hong gave some kind of one generalization of the method, which is called the orthogonal method. It captures some combinatorial of two symmetric matrices. And in this talk, I will focusing on some another generalization of the method, which captures the combinatorial properties of the symmetric matrices. So before to do that, so let's just show, recap some historical background about the matroid coefficient and something at others, some AKA Baker-Bonus theory. So the first one is the matroid coefficient in fuzzy ring, which was first founded by Dress and also studied by Dress and Wendell. So in this line of research, also they first introduced valuated matroid. And so another line of the research, which is quite related with the Baker-Bonus theory, is the partial field representation, which is extensively studied by those kind of groups. And maybe it is worth to remark that the paper by Paddington and Van Zhang, their paper about the lead theorem for the matroid is quite related with the foundation of the matroid. And then actually 5 years ago, Matt and Nathan, they unified those kind of two concepts and introduced the matroid with coefficient in tract. And also they provide several equivalent definition of the matroid coefficient. So in the original paper by Dress, they only using the one definition. It just comes from the Grassmann-Plicker relation, but the paper by Dan and Bowler gives some another definition, something like F circuit set and which is quite related with the signed circuit of the oriented matroid or the tropical linear space. So depending on the definition, what you like. And Tong already said that I and Tong did some kind of another generalization regarding the skew-symmetric matrices, and also Manuel Jara and Oliver also give some another way to generalize this kind of concept, which called the flag matroid coefficient. And here, so in the case of the orthogonal matroid, this is realized by the skew-symmetric matrices. And one may wonder that then how about the symmetric matrices? Can we do something delta matroid coefficient, since many people think that delta matroid as a combinatorial counterpart of the symmetric matrices? And I will give some certain amount of affirmative answer for this question. So actually, I will introduce some another generalization of the matroid, which is quite related with the delta matroid. And also, on the half of the talk, I will introduce the antisymmetric matroid coefficient by just observing certain quadratic relations. And also, I will give some equivalent to cryptomorphic definition as well. And also, I will see some connection with the another topics, such like Gaussoid or the symplectic Dressian defined by some another group of researchers. Okay, so let's start. So this is everyone knows. So the matroid is nothing but a pair of the element, finite set of element, and which satisfying the basis exchange axiom. However, we also know that this satisfying the strong basis exchange axiom, which is described in there. And this is quite related with the Grassmann-Plicker relation. So if you consider about the linear matroid, which is realized by the R by N full length matrix, and then if you just convert this into I'm collecting all maximally independent columns, then this forms the basis of the matroid. And the Grassmann-Plicker relation is quite well-known fact about well-known quadratic identities for these maximal minors. And maybe it is better to make it more precise. So we already know that. Let's take this as our basis, and then we just choose our B1 and B2 here. And also we fix E first, and then let's take PS as a P2 plus E and T as a P1 minus E. And then you can check that when X is equal to E, then is nothing but XP1 times xb2 and with a certain sign. And then also it just some another element which is in here. So since we already know that this is non-zero, so to satisfy this is zero identity, we always find some another element f which satisfying the Grassmann-Polykel relations. And for the even delta matroid case or orthogonal matroid, or maybe it is also worth to note that this is actually defined much, 10 years earlier than the delta matroid, which name is Fabian structure by Joseph Kuhn. So yeah, it satisfies the following axiom. So if an even delta matroid is the same as the matroid, we have some finite set and some non-empty collection of the bases, and which satisfy the strong base exchange axiom. But here we just replace the set difference by the symmetric difference. And here, if you just neglect the blue colored part, then you just get the axiom for the delta matroid. Okay, so one typical example is, of course, matroid. So matroid is nothing but a even delta matroid of which bases have exactly the same cardinality. And some linear cases just comes from the skew symmetric matrix as Tom introduced. So if you just consider the n by n matrix and collect all non-singular principal minors, then you can obtain the even delta matroid. But it is also quite related with the weak relation, which is also kind of quadratic identities for the Fabians. And actually, you can easily observe that this is a generalization of generalized Grassmann-Polykel relation as well. So then our remaining question is then, what is for the symmetric matrix? Do we have any analog of the Fabian or any quadratic relations? And do we have some combinatorial object which captures those kind of quadratic identities, so which possess the strong base exchange?
What's the Fabian again?
Sorry?
What's the Fabian?
So Fabian is, how may I say? So it is determined, it is defined over the skew symmetric matrix, and it just, when for the, you can consider some graphs on the, whose vertices are the n 1 to n, and you consider what the matchings. And so matchings, each edges are just labeled by the rate on which described in the entry I and j. And so you use just sum of the all matchings with, weighted matchings with certain sign, then you get the determinant. So because of these signs, and it is very closely related to the determinant. And also one other thing is, if you just consider what the scale of the determinant, then it is equal to the scale of the Fabian, then it is equal to the Fabian determinant. Sorry.
That's the canonical square root of the determinant for skew symmetric.
And yeah, so one may think that, oh, maybe delta matroid could be a good candidate, but there is some bad counter example. So if you just consider about this symmetric matrix over any field of characteristic other than 2, then if you collect all principal minors, non-singular principal minors, then we have these 5 bases. And then we take the empty set as a base and the 1 to 3 as also base. And then you can easily check that there is no F such that both are bases. And so delta matroid, even for the representable delta matroid, it does not satisfy the basic exchange axiom. And this implies that if our delta matroid is support of the certain point parameterized in the symmetric matrix in the projective space, then it must satisfy certain quadratic relation or some homogeneous relation. But since it does not satisfy the strong base exchange, so it cannot be. And another important observation is, if even you have some old information about the principal minors, you cannot recover your original matrix. So this is very simple counterexample. And actually, this can be easily resolved if you consider all the almost principal minors as well. So almost principal minor is just nothing but the columns and the rows are just off by 1. So actually, this kind of things, using this kind of observation, Boege, Darley, Carr, and Stamford, parameterizing the Lagrangian symplectic Grassmannian into the projective space with some reasonable dimension in the reasonable dimension projective space. Yep. Is there any question up to now? And then almost principal minors. If you consider the almost principal minor, which entries by rows are I and rows are J, then this is Aij. So this obviously we can recover our symmetric matrices. And not only this, also you can find some certain good quadratic relation just consider about the Laplace expansion for the symmetric matrices, which only concerning the principal minors and almost principal minors. So if you just consider the Laplace expansion with fixing this ith row, then you can get everything on the right-hand side is either the principal minors and almost principal minors. And also, if you just having if you're just starting from the almost principal minor, then still you can get some similar result. And actually, this can be this relations are. We have two different relations, but we can make it as one single formula. This is quite simple. So before to do that, so let's convert our index row and column indices in the n element set. So we'll just have some R rows and C columns, then we just convert into the n minus R plus C star. So here, so we just rather than we consider the n element, we just copying and duplicate our ground set with the star element, which is also you saw from the construct. So and then there is one obvious bijection between those. And in the case when R and C are equal, then this is the transversal, which was there in the Tonstalk. And also we should do some another case when R and C is just off by 1. And we will call this as an almost transversal later. And also another good observation is if we just consider attaching some identity matrix on the left-hand side, depending on the combination, we can also attaching the right-hand side, but whatever, then determinant of this matrix is also equal to the determinant of the right-hand side, so which is the maximal minor of this n by 2n matrix of the sign. And moreover, if those kind of two quadratic identities can be written in the one single formula, which is just Grassmann-Plickel relation, but you only observe some certain cases. So here we assume some additional condition that S contains exactly one element I, so that I and I star together, which was called in the skew pair, and T does not contain any skew pair. In this case, you can easily observe that T's and S minus X and T minus X, S minus X and T plus X is always the principal, principal minors or the almost principal minors. Yeah, and then let's do some combinatorics. So you just, as we saw the relation between the Grassmann-Plickel relation and the strong basic exchange action, we can do same things. So before to do that, we fix some notation. So here Tn and curly Tn is the set of the transversal, and the curly An is almost transversal. So actually, the above one transversal stand for the principal minors, and the bottom one, the almost transversals, represent the almost principal minors. And we call also I and I star is a skew pair. And an antisymmetric matroid is nothing but some 2n element ground set together with the basis set of the non-empty family of the basis, which satisfying the following two conditions. So the first one say that if you have some one basis, then you also have its transpose as well. So this is stand for the symmetry of our symmetric matrices. And the second one just captures the combinatorial properties of our restricted Grassmann-Plickel relations. And yeah. So, and you can easily convert this into some more familiar language. If we just choosing S and T just carefully, then you can check that, oh, this can be converted into this language. So if we have some any basis and pick any element from the one set difference, then if it satisfies certain condition, then we can always find F, another F, so that B1 minus E plus F and B2 plus E minus F are both our bases. Is it okay?
Sorry, can you explain what you mean by transversals and almost transversals in this context?
So yeah. So here I observe that there is one-to-one bijection between the columns, and we can convert these rows and column indices to the n element set in this ground set. And when R and C is equal, then this means that when we consider the matrix, which is indexed by this, then this means that the principal submatrices. And the corresponding thing for when R and C is equal, we call the transversal. And when R and C are just with the same size, but the size, the only one element different. If you consider the symmetric difference, then this different by two elements, but whatever, then in this case, this stands for if you consider the ARC, then this is the almost principal submatrices. And
Okay, I see. Okay, thank you.
Sorry, I don't mean to be snarky or anything, but even delta matroids correspond to antisymmetric matrices, and antisymmetric matroids correspond to symmetric matrices.
So yeah,
Is that right?
that's a nice question. So there are many reasons. So first, there are already symmetric matroid by Boege. And also there is already symplectic matroid by, if you see the Coxeter matroid book. So I should find something else. So also the reason why is if you consider what the matrix case, then it makes opposite. But if you consider the vector space, Lagrangian vector space, when we consider also bilinear form, then this antisymmetric matroid equipped the Lagrangian equipped with just comes from the Lagrangian subspace equipped with the antisymmetric bilinear form. So I just followed this bilinear form. Thank you. Okay, no question? Is there any more questions? Okay.
So if you project this onto just the transversals, do you get back the axioms for delta matroids?
That's a nice question. Yeah, that's true. Okay. Not only the representative case, it is widely true even for the non-representative case.
Does every delta matroid arise in this way? Like, so you forget, like, I understood if you forget about this almost transversals, then you get a delta matroid?
Yes.
Can you get every delta matroid in this way?
I don't know about this case. So this is open for me.
But many different things can define the same delta matrix.
A different antisymmetric matroid, yeah, that also may happen, even for the representative case. Yeah, this some kind of canonical map from the class of the antisymmetric matroid to the delta matroid is not injective, and we don't know whether this is surjective.
What happens if you forget the others? What happens if you forget the transversal?
Oh, that's also a nice question. So if you assume something more about that, if you our antisymmetric matroid contains every transversal, and with this assumption, if you just discard all transversal, then this is nothing but a Gaussian, which is defined by sorry, I cannot remember the author's name, but which is Gaussian, which captures some combinatorial properties of the positive definite matrix it captures some when the almost principal minors are singular simultaneously. So yeah. Okay, so maybe let's go. Since there's an answer about the last question or so. Yeah. So representative case, yeah, you can easily check this, and this is without the representative case, we always can obtain antisymmetric, delta metroid from the antisymmetric metroid. And or not only this, so if you just assume that we have some metroid, then we can also always construct some suitable antisymmetric metroid. So just if you have base, then you can just construct the corresponding transversal, and also you if you two bases are just off by one, what I mean is in this case, then this is almost transversal, and we put everything in this case. And this pair, this collection of the transversals and almost transversal satisfy the axiom of the antisymmetric metroid. And not only that metroid, also even delta metroid satisfy this kind of observation as well. So this is actually, I will explain a little bit later, but this is quite related with the Krasner hyperfield. In the Krasner hyperfield, -1 is equal to 1. So as you know that in the field of characteristic 2, every skew symmetric matrix, what I mean is zero diagonals, is always a symmetric matrix.
If I have an even delta matrix, is this the unique way to?
Yes, unique. That's also a good question.
Finish your sentence.
To construct an antisymmetric matrix.
Yeah. I already give so many clue to convincing you that this is some kind of good object, but also I can give you some another reason. So this is quite related with this is what Tom mentioned. But Todd's first idea in the Tom's talk, this is equivalent statement. So if you have some, in the case of the matroid case, let's see. So if you some vector satisfying or point in the projective space satisfying the all Grassmann-Polyker relation, then actually it can be recovered from the 3-term Grassmann-Polyker relation with some additional assumption about the matroid, regarding matroid. And similar things happen for the antisymmetric matroid as well. So if our vector satisfying the restricted Grassmann-Polyker relation, if and only if is satisfying all 3 and 4-term restricted Grassmann-Polyker relation together with the support is the set of the basis of the antisymmetric matrix. And there also one thing to point out that so here 3-term is not enough. We need 4 terms. And yeah, also one second remark is you can observe the similar phenomena for the orthogonal method and the weak relations, and maybe you can check paper by Matt and Tom. Okay. So I say in the third page, I say that it can be defined also circuit as well. So let's define the circuit of the antisymmetric matroid. So here circuit is the same as the matroid case. If the minimal subset, I just forgot the minimal. Yes. Minimal subset not containing any base, and it also contains at most one skew pair. So if our C contains something like I and I star together with the J and J star, then it is not we just neglect these cases. So if you consider any row space of this n by 2n matrix, and if you collect all minimal support, which is satisfying this condition, supports contains at most one skew pair, then actually it is not that hard to show that this satisfying this forms the circuits of the antisymmetric matrix. To do that, maybe it is worth to mention there is some circuit axiom, cryptomorphic circuit axiom for the antisymmetric matroid. So our family of the subsets, which satisfying some trivial condition, is a circuit of the antisymmetric matroid if and only is satisfying certain trivial condition together with the orthogonality and also maximality in condition. So here orthogonality condition just stand for our row spaces. In here is Lagrangian and isotropy, and this set just stand for this is n-dimensional. So this is kind of combinatorial interpretation of that. And you also look at, this is looks very similar to the Mintis painting axiom for the Matroid or self-dual action for the Matroid. So if you just collect the set of the family of the circuits and the family of the co-circuit, then it actually satisfies those conditions where the second one usually called the orthogonality to the Matroid. And also if you just have some two family of the sets which satisfy this, then we can also recover our original Matroid as well. And in this view, also very similar to the Thom's talk, I mean, the relation between the orthogonal Matroid and the Matroid, you can observe that the collection of the circuit together with the collection of the co-circuit with the star, then it satisfies both these conditions. So this is actually the antisymmetric Matroid.
Why is it called painting?
So the reason why it's called painting is because of this part. So you just color this red, this blue, and greens, and so on. Yeah. So this is, I think this is the reason. Yeah. Yeah. And any other question? Yeah, maybe also it is worth to note that if you have some vector space, I mean some r-dimensional vector space in our ambient n-dimensional vector space, and then you have some very canonical map to make it as a Lagrangian subspace in the 2n-dimensional vector space. You hit with some antisymmetric bilinear form, and actually this is some kind of very similar to this. Okay, so yeah, this was the half of my talk, and yeah, let's move to the antisymmetric Matroid with coefficient in tract. So take up all theory for the Lagrangian Grassmannian. So first, let's review some definition about the tract. So we already reviewed the pastures, and this is a little bit different. So pasture was observed some three-term Grassmann pellicle relation, and tract actually introduced a little bit, maybe 1 or 2 years earlier than the pasture. It captures the whole Grassmann pellicle relations. So the definition is it is some kind of multiplicative monoid with some observing element 0 and just abelian multiplicative group together with some which called null set which observing what is 0. So it is just a subset of our group semi-ring satisfying those conditions. Okay, so the first condition said 0 is in the null set, of course, and every non-zero element is not in the null set. And the third one means that there is unique epsilon, so that 1 plus epsilon is in the null set. What it means is we can consider epsilon as a -1, and there is some trivial group action. Okay, so maybe it is better to look at the example. So if you have some given field, then as a set or the multiplicative monoid, we just follow the usual multiplication of the field, but the null set is constructed from the every formal sums, which are sums to 0 in our original field. And for the case of the Krasner hyperfield, so it has only 2 elements, 0 and 1. Here, 1 actually stands for the non-zero elements. So maybe you can consider it as a, yeah. And if you consider about the sum of the 2 non-zero elements, then it can be 0, right? And also some 3 non-zero elements, also it can be 0. So this actually captures this kind of properties. And also sign hyperfield. So if you just consider about the 0 and plus -1, and here +1 just means the positive element, and the -1 is negative element in the real field. And then you can easily check that, positive number plus positive number cannot be a 0, but positive plus negative can be a 0. And so on the other extreme side, you can also consider the regular partial field, which ground set looks same, but it captures a totally different phenomena. So So 0, I mean, each null set is something like 0 or 1 plus minus 1 or and so on. So this means that if you just sum of these former sums of the 1 and minus 1 in our integer link, then if this is when 0, then we just capture directly this and put this into our null set. And yeah, tropical hyperfield you can define this way. Maybe people who are working in the tropical geometry know why this definition is reasonable and better than me.
You show us something that's not a pasture.
So okay. So maybe this is not direct answer, but if you just, since this is a little bit different, so if you just have any track f, so which just given by with the nf null set, and we have some natural, we can construct a natural pasture which discarding all former sum with at least four terms. So if you just consider only the 3 terms, then you get the pastures. And there is some cases from 2 different tracks may result in the same track. So
Same pasture.
yeah, same pasture. So for example, is the regular partial field, and there is a product of the track, and they are different in the track, but they are equivalent to the pasture, and this is quite important observation to understand the foundation or the representation of the method.
There's also a functor going the other way, from pasture to tracts.
Okay, I'm not that well known where, so maybe we can ask to someone, yeah, Oliver or Matt. Yeah.
Adjoint functors, and you can say that a tract is a pasture if it's kind of in that image of that.
Yes.
That,
But that functor does not preserve products.
right.
Yeah, I think so. In the pasture, yeah, F2 times F3 is equivalent to the regular partial field, but in the track, it's not true.
So is one a full subcategory of another, or none of the
Yeah, that's just our full interest.
pastures are full in track?
Drax is the logic.
Surgical pasteurization.
Yeah, that's in one of my papers with Oliver. I wish we had saved that term. We used it in a slightly obscure context, and now we can't reuse it in a more popular way.
Okay, thank you for the support. Let's go to some another result by Matt. So yeah, Matt and Nathan define the F matroid, or another way, matroid with coefficient in track F. It's nothing but some kind of point in the projective space. We can, of course, since we have some particularly monoids, so we can consider some, in some sense, projective space, and we satisfying the just Grassmann-Flicker relation over the track. So here we just replace the equal to 0 by the it is in the null set. So it makes sense if you consider about the field. So F matroid is nothing but just representation, flicker vector in the space. So it is nothing but a linear space over the field F. And the Grassmann hyperfield, for the Grassmann hyperfield, K matroid is just equivalent to the ordinary matroid, as we observe, and so on. So S matroid or the sign hyperfield is equivalent to the oriented matroid, and over the tropical hyperfield is equivalent to the valuated matroid, and for the regular partial field is equivalent to the regular matroid. And also this is due to that there is a unique representation of the regular matroid. So yeah, why not? We can define the antisymmetric F matroid as well. So very similar way. So first we just fix any point, which satisfying some for the following condition. Actually, maybe you wonder that why sign looks very weird, but this is some computational reason, so let's relax. But whatever this condition actually stand for the, it comes from the symmetric matrix. So yeah, this means that the transpose of determinant of transpose is same as the original one. And the second one is just consider the restricted Grassmann-Pilical relation over the over the any arbitrary tract F. Okay. In this case, because our definition, antisymmetric K matroid is just equivalent to our original antisymmetric matroid. And when we consider it over the field, then it is actually some vector which satisfies the restricted Grassmann-Pilical relation. And so it is equivalent to the Lagrangian subspace, or which is, or one another reformulation is n by 2n matrix, which is satisfying these conditions. And we have some another conditions, just comes from the circuits. So if you have some like I by A, here A is a symmetric matrix, and if you collect the all minimal support of the non-zero vectors, which is satisfying that it contains at most one skew pair. And we already observed that this gives us circuits of the antisymmetric matroid. And if we just put some elements on there, so if we just collect all vectors, which is satisfying the which support is the circuit of the antisymmetric matroid, then actually this is our definition of the antisymmetric F circuit set. So more precisely, it's satisfying this condition, and the last one stands for this comes from the Lagrangian subspace equipped with the antisymmetric bilinear form.
I have a question on the previous slide.
Yes.
So if you have a valuated matroid, which is a T matroid, that gives you a tropical linear space.
Yes.
So if you have an antisymmetric matroid over the tropical over T, does that give you like some kind of version of a tropical linear space with a symmetric form on it?
This is quite related. So it is something like, if you consider about the n-dimensional tropical linear space, which is defined in the 2n-dimensional space, and if you're just only collecting the certain circuits or certain vectors, then not every vector, then it forms the antisymmetric T matroid. Maybe I will explain this a little bit later on. Yeah, but this is in some sense very related. But yeah, so also one other thing what I want to say is antisymmetric T matroid. I mean, oh no, the other way. So every valuated matroid can be viewed as a antisymmetric T matroid. But maybe it is hard to consider about the other way around. Thank you for the question. And this was the definition of our antisymmetric circuit set. And yeah, this is quite, maybe this is more look similar to the tropical linear space if you consider its definition over the tropical hyperfield. And actually what I show is there is one-to-one bijection between the antisymmetric F matroid and the antisymmetric F circuit set. This is very similar to this is some direct analog of the F matroid in terms of the Grassmann-Pilical relations are equivalent to the F circuit set of the matroid. And yeah, if you just consider our F as a Grassmann hyperfield K, then this is nothing but a cryptomorphism between the basis and the circuits. And if we pick our F as a field, then actually this part is nothing but it's corresponding to the Lagrangian subspace. And yeah, this is nothing but a point in which is satisfying the restricted Grassmann-Pilical relation. So it actually gives the parameterization of the Lagrangian Grassmann-Pilical relation over this dimensional vector space. and this dimensional projective space. And actually, not only this, actually this map was given by this paper by Boege, Carr, and Stanford. And what I showed is actually this is cut out, set theoretically cut out by the Grassmann relation, and these kind of things are observed for the general tract.
There's also a distinction between weak and strong antisymmetry.
So yeah, that's also a good question. So because because of here, we can also define the weak antisymmetric F matroid using the 3 and 4 term Grassmann restricted Grassmann relation. And but I don't know whether this is coincide when if we choose rather than the field, if we choose like tropical hyperfield or sine hyperfield, I don't know yet. This is coincide. So maybe it is worth to mention that in the proof we use some kind of homotopy theorem. So in the previous talk, Tom mentioned about she didn't mention exactly the third homotopy theorem, but it is quite related to the touch homotopy theorem. And actually, in my mind, there are exactly two homotopy theorems in Matroid theory. One is the touch, and the other is Mauler's homotopy theorem, which is which is related to the base graph of the Matroid. And we actually proved that it's generalization of the Mauler's homotopy theorem. So for the given antisymmetric Matroid, and we just define a transversal base graph, of which base are just transversal bases, and we give an edge relation when the difference between the bases are just 1, or this is equal to 2 with a certain additional condition, but maybe if you don't want, you can neglect. And also weight of the edges is nothing but a difference. And then what I showed is homologic group is generated by the cycles of weight and most A. And if you just consider the Matroid and its base graph, then it's the cycles of length M4 is just corresponding to the weight of cycles of weight 8 and 6, then 3 corresponding to the weight 6. So it directly implies the Mauler's homotopy theorem. And yeah, is there any question?
Right, how is the weight of a circuit defined?
Sorry. So this is if you have this, if edges of this is something like E1, E2, En, then this is just nothing but a summation of E1, Eis. Thank you. Yeah, thank you for questions.
And the point is that that is needed, that homotopy theorem is used in the proof of the previous.
Yes. Yeah, that is used in this theorem. So wait, so this direction is quite obvious. And when we prove that this direction, and one funny thing is for the case of the field, if you just consider, this parameterization, this part is easier for me, and this part is a little bit harder than that. But on the general track, it is totally different the other way around.
So presumably BOKS did not need to something like that when they put their result over field.
Okay. Sorry, 4 people, but yeah. So actually, they do not show that this is set theoretically cut out by the restricted Grassmann relation. They only see that this is some well-defined. This map is well-defined and give the projective variety, and they also show that it's defining idea. If you consider only the quadratic relation of the defining idea, then this actually they show that this is scheme theoretically cut out our Lagrangian symplectic Grassmannian, but they do not give the explicit list of these things.
So this theorem is even new for the case when F is a field.
Yes, this part is new for even for the field.
I see. And you need homotopy statement to prove that.
For the field, no, you don't need anything. So this is actually not that hard program. And yeah, and also yeah, but if you consider about the general tract, I mean more like or hyperfield, then you need homotopy theorem. I mean this is maybe it is worth to say that this is comes from the well-definedness. I mean, to this side, homotopy theorem is used for the well-definedness to show the well-definedness of the F matrix. But in the case of the field, this is nothing but you can consider this as just a matrix. So everything's are trivial. Thank you. And yeah, these are the last one. So as we see, let's see some related concepts. So as we already asked by some audience, this is quite related with the delta matroid and also for the Gaussian. And another observation is antisymmetric matroid over the sign hyperfield generalized oriented matroid. In the paper by Booth, Borovic, Gelfand, and White, which name is oriented Lagrangian matroid. Here Lagrangian matroid is nothing but when people say about the Lagrangian matroid, this is equivalent to the delta matroid, and they define the oriented version of the Lagrangian matroid, but which does not generalize oriented matroid. So in some sense, it is not satisfactory some answer. So, but in our case, we generalize oriented matroid. And so maybe you can consider you can try to consider about some kind of analog theorem from the oriented matroid to the oriented antisymmetric matroid. And also, this is quite related with the valuated matroid. So maybe look at this example a little bit more. Some audience asked. So there is one with the tropical linear space and also the valuated matroid. So in the paper by Bora and Orlato, they defined the symplectic Dressian or the Lagrangian symplectic Dressian, so which is nothing but a valuated matroid and rank n valuated matroid on the 2n elements ground set together with the certain linear relations. Just that linear relations just comes from the parameterization of the Lagrangian symplectic Grassmannian into the space of the n choose n dimensional projective space. Yeah, but it contains too many information. So if you just discard every information except the transversal and almost transversal, then you can get the antisymmetric T matroid.
A union, like TN union?
Oh, sorry. Otherwise, this is empty. So thanks. And also, it's related with the Laplace paper, and they extend the Laplace definition a little bit and define the isotropical linear space. So this is nothing but a tropical linear space with some orthogonality condition in the tropical hyperfield or tropical sense. And then if you just collect all vectors which support this satisfying the contains the most ones Q pair, this forms in the case of the field, it just forms the antisymmetric matroid, and this is also generally true for the valuated antisymmetric circuit set. And in their paper, they show that those two concepts are equivalent when n is most 3, but this is generally not true. If I remember correctly, both sides are not true. But if you just discard certain amount of information and you just preserve the essential information, then you can easily check that not easily, but what I mean is from our equivalent definition of the antisymmetric antisymmetric F matroid, we can get those equivalent things. That's all my talk. Thank you.
Questions? So I have a question relating to the last things you said, because I'm a little confused. So antisymmetric matrices, do they appear both in B inside B?
Sorry, what?
Now, which Coxeter, antisymmetric matrix appear in which Coxeter type?
I think it corresponds to the type C. Type C is something like
Yeah.
n-dimensional spaces in the 2-dimensional, right? So yeah, that's what I think about. And yeah. But yeah, in the case of when track is in the track, if one is -1, then actually it contains the type D case. I mean,
Yeah.
you know that, or also the delta matroid contains even delta matroid, some similar phenomena in general.
Yes.
The plural relations that you're writing down, are those the plural relations in the minimal embedding of the Lagrangian Grassmannian?
What is the meaning of this?
So you have to take essentially sections of one. Like for Grassmannians, the
Yes.
minimal embedding it's inside the fundamental representation for wedge chaos here. In symplectic case, it's the fundamental representation corresponding to the last node.
Sorry, I don't know this fundamental things, and
Alright, so then maybe.
maybe we just discuss earlier later. I think.
The answer is no. It's no. Okay, the answer is no.
Other questions?
Is there some way of characterizing these antisymmetric matrices in terms of polytopes?
Oh yeah, there was some
Subdivisions?
Yeah, so actually when Ted and Oliver visited June, and then we also I just went so and we discussed something a little bit. And yeah, so one natural way to consider about the polytope is something like if you just have some basis, then you can just put the characteristic vector for that. One important thing is when we consider about the polytopes of the delta matrix, we just consider what because we have some basis, something like 1, 2, 3 star 4, then we assign this as a E1 plus E2 minus E3 plus E4. And for the case of the antisymmetric matrix, we can consider something similar, same things, and consider the complex pool. And then actually, if you only consider its support, then it is exact. If you just consider only its convex rule, what I mean is forget every original vectors, then it is just exactly equivalent to the original matroid, delta matrix. So every antisymmetric matroid lies in the just exactly middle, or on the middle of the face, whose vertex is transversal. There's transversal and almost transversal bases are just in the middle. So, but also this gives something funny phenomena, but yeah, I didn't research much on.
Somehow what was done previously by Gelfand, Serganova et al. Was to kind of take the obvious generalization in type C of the polytope break condition, and that gives you some notion of symplectic matroids, but all these other things he mentioned are sort of bad properties of symplectic matroid. Orthogonal matroids are quite good. Symplectic matroids is sort of bad in various ways. And Olarte et al. Had all these counterexamples. And so by giving up on that polytopal point of view and changing the perspective, Donggyu found like a different definition in type C, which is maybe bad from that point of view, but has other much better. Seems like you have to choose what you want in type C. In A and D, don't have to choose. You get everything perfect.
Maybe also it is already worth to mention that. So in the case of in the delta matroid polytope, the edge length might be different 1 or 2, but in this case, if you just subdivide this, then always the edge lengths are 1 in some sense. Maybe this would be useful in future direction. I don't know. Yeah. Maybe.
Oh, sorry, this question, not really much of a question, more like follow up on this. Is there some, like a specific example of like something you might try to extrapolate from a matrix polytope point of view, and then you try to generalize this to antisymmetric matrix, and then something goes wrong? Like, can you give a specific?
When I said it's bad,
Yeah, or maybe
just
like from
we
like,
weren't able to find like a nice simple description of which polytopes arise as
okay,
the matroid polytopes of antisymmetric. Maybe there is such a thing, but it's not.
Yeah, we don't know yet.
But in the valuated case, if you have these like interior lattice points and you think about the valuation as like lifting them, and as you lift the interior points, that's gonna change the subdivision you get. Potentially.
We were thinking about it.
Yes, but one important thing is even you lift, still this point lies in the line between the two vertices. So it always the same thing. But one thing is if you have some middle interface, then it gives that either you just fold this way or the other way. But however, if you don't have any almost transversal basis with this space, which all everything's are this, then you cannot fold this. This is a little bit different. Yeah.
I see.
More questions? Everybody hungry? Okay, then let's think.